Professor Brady will present two talks, as is the custom of the Smith Lecture Series. The first talk, which will be given today, is entitled The Micromechanics of Colloidal Dispersion. Tomorrow, he'll present the second talk, to a somewhat more general format, Chemical Swimming and Active Matter. Please join me in welcoming Professor Brady to Cornell and to the podium. John?
Thank you very much, Lyndon, for the kind words. It's a great pleasure to be here and to be amongst friends and colleagues. I hope you can all hear me. I'm mic'd apparently for that, but not for the rest of the room. But so if you can't hear me, then just please shout out. I'm really pleased to be here and to give these lectures today and tomorrow. It's warm in the room, so if you don't mind, I'm going to take off my jacket before I get started. And please feel free to do that as well. So just sit back and relax. I'm going to try to tell you a story about the mechanics of colloids, at least how we think about them. And at the end, a lot of students have contributed and a lot of people have supported this work over the years. And at the end, I will acknowledge those that have done the work rather than at the very beginning. I'll say at the outset, neither Don Koch nor Rosanna Zia had anything to do with what I'm going to tell you about today. So don't blame them. That's all. OK, so here's an outline for the talk. What's a colloid and why do we care? And then how is this a problem in fluid mechanics? You can insert chemical engineering instead of fluid mechanics if you wish. And then I want to talk about what I call the amazing rheology of spheres. You might not think that's amazing, or how to walk on water and make a bulletproof vest. When I made the outline, I was very ambitious, and I had some other topics. How does random diffusion demix a suspension? And then what can we do with active matter? Active matter will be a discussion tomorrow, so we won't cover that today at all. And I hope to be able to talk about how does diffusion demix something, but we'll see how we go. And if we don't have time, we'll just stop when time's up. So let me begin with what's a colloid and why do we care? So as many of you know, colloids are just small particles dispersed in a liquid. They come in a variety of sizes and shapes and colors, as you can see. And the colloid scientist is able to make all kinds of interesting things for us these days. And what sets them apart, or what's distinguishing the feature about them, is the fact that they're small. And small means, say, 10 nanometers to about 10 microns or so in size. And because of their small size, they're subject to the thermal fluctuations in the solvent characterized by thermal energy KT. And that gives rise to what's called Brownian motion. And we'll talk a little bit about that. Those thermal energy compete against any kind of interparticle forces that may be operative. They might just be excluded volume forces, for example, as well as with the fluid flow or the hydrodynamics. And the competition between the thermal forces, the interparticle forces, and the fluid flow is what sets the structure of the material that you make from these colloids and determines their properties. And so I want to walk you down the path about what can you think about these wonderful variety of shapes and sizes and how their properties determined by the interplay of thermal forces, interparticle forces, and hydrodynamics. So that's what they are. And actually, people can make all kinds of fun things these days. You can actually tailor particles which then interact with each other. So they actually can form and assemble and form a colloidal molecule. So rather than the building block be an atom, the actual building block be a colloidal particle. And they'll actually assemble together in nice chemical reaction networks, just like you might be thinking about from a normal chemical reaction. Why do we care? We care because they occur around us all the time. Lots of things were everyday experiences such as paints, blood flow, milk. I think everyone today has either eaten or drunk a colloid. You may not know that, but you have. If not, go have a glass of milk and you'll have. And so they're around us all everyday kinds of things, as well as other nice materials. You might be interested in making materials which are very nice in properties. Maybe they might be nice mechanical, thermal, or optical properties by controlling, rather than building them up from a molecular level, already build them up from colloids, which already are, say, an example of the wavelength of light, and therefore they might be a bit better able to make something that's nice and visible. And so here I have a nice picture from the Physics Today many years ago in honor of Easter, these nice Easter egg kind of shapes. Those nice solids are actually 98% water. Okay? A tiny little bit of particle, you tune the interactions, and you make a solid which is essentially out of water. It's a very weak solid, but nonetheless a solid. And so one is interested in trying to understand how you can control and manipulate materials that may look like that. I also have in here printing ink as a colloid. It turns out that's the most expensive fluid you can buy. Now you actually all know that because anytime you go buy toner for your printer, it's very, very expensive, right? They'll give you the printer for free. They want you to buy the ink and the paper instead, right? Okay, so it turns out it's more expensive than Chanel No. 5. So there could be some interesting things in understanding how colloids behave to kind of make money, for example, is a good thing to make. And so the other aspect of colloids is they're what's called soft matter. That is, many soft materials either are or can be modeled as colloids. Again, it's just a repeat of the competition between thermal energy interparticle forces. But what makes them interesting is the fact they're soft. And what I mean by soft is the following. Most materials, atomic and molecular materials made out of molecules, like this table here, the strength of the material is actually proportional to the number density of particles that are inside there, for the same level of interactions. And so for a colloidal material, the colloidal particles are much larger than solvent or molecular sized objects. And the ratio of the strength of a colloidal material to that of a comparable atomic material scales like the size ratio cubed. They're much weaker by that ratio just because there are fewer particles per unit volume. A very simple idea. At the same time, the time scales for their motion are much slower than the time scales for molecular systems. And that also scales like the size ratio cubed. So if you think about trying to actually distort or deform this solid material, you require enormous shear stresses, and the time scales are femtoseconds over which the deformation occurs, whereas something like a nice colloid you can distort with your fingers. Okay, so the time scales are all slowed down to our seconds time scale, as well as the strength of the materials are much weaker, and that makes them interesting. Actually, we're all composed of a lot of colloidal stuff. That's why we're soft and squishy and move around on those time scales. As a result, also, it's very easy to drive them far out of equilibrium. Okay? So those are the important features I want you to recall. And so now, why is it a problem in fluid mechanics or chemical engineering? And that we blame on this guy here, Einstein. And why do we blame it on him? Was because there were some experiments done by a guy named Robert Brown back in the 1800s about a phenomenon called Brownian motion. And these are some examples of what Robert Brown did was look at small pollen particles undergoing random, what's called today Brownian motion. His interest at the time was in what he called the motive force of life. People thought living things had some special property. And so he was interested in actually the spores of a pollen and how they jiggled around, and thought he had discovered what was the true motive force of life. That actually carried the genetic information in the spores of the pollen. But being the good scientist that he was, he also did the experiment not just with the pollen particles, but also with coal dust and ground up stone and other things, and found that they all too did the same random walk process. And so he was disappointed. He didn't discover the motive force of life. But being the good scientist that he was, he wrote up his observations and published his work. You know, even if it's a negative result, still publish it. Okay, it's always good. And the title of his paper is great. It's like on the observations of the motion of particles during the months of October, November, December. You know, one of those kind of papers like that. And Einstein came along and realized that that phenomenon of Brownian motion is related to diffusion. That is, the mean square displacement of one of these particles, if you tag it and watch it wander around, grows linearly in time with a constant of the diffusivity d. And what Einstein did was be able to relate that diffusion to the thermal energy kT and what's called the hydrodynamic mobility, how fast a particle moves in response to a force. And where he got that mobility from was from this guy over here, Stokes. Stokes had worked out the relationship between the hydrodynamic drag force on a particle and its velocity. And that force is proportional to the viscosity of the suspending fluid and the size of the particle. That's a result at what's called small Reynolds numbers. And putting those two together, we get the famous Stokes-Einstein relationship, which relates the translational diffusivity to the thermal energy and the Stokes drag. Okay? A very famous formula, which I hope you'll, if you don't know already, you'll put in your memory bank, which is unerasable. Okay? A little bit of a historical note. At the same time that Einstein wrote this paper in 1905, there was a publication by another person named Sutherland who did the exact same thing, had the exact same route, and this is a copy of his paper. And his paper is actually easier to read than Einstein's paper, not only because it's in English, but because it actually is quite a very simple explanation and derivation of this famous formula. And as far as I know, Sutherland is unknown to science. So who knows about Sutherland in the audience? Rosanna, not allowed to raise your hand. Ite, guys, you guys are a few, okay? But most people don't know Sutherland at all. So I want you to remember Sutherland. And so I know that it's a mouthful, but please attach Sutherland's name to the Stokes-Einstein-Sutherland formula. He did it at the exact same time. So that's a little bit background on Brownian motion and diffusion. At the same time, in that same famous year, Einstein did another calculation, not only Brownian motion, diffusion coefficient. He also worried about the effective viscosity of a dilute suspension of spherical particles. And he showed that viscosity was increased by adding particles, and that increase was proportional to, was 5/2 times the volume fraction phi, the volume fraction being the number density times the particle size cubed. And notice there's a correction in 1911, because Einstein got it wrong the first time he did it. Okay, so that's just to reassure everybody in the audience, you know, the fluid mechanics can be hard sometimes. Even Einstein got the wrong answer the first time. So at this point, you know, you might be wondering, you know, what was Einstein doing in 1905 worrying about Brownian motion and the viscosity of a suspension of spheres? I mean, didn't he have something better to do, like relativity theory or E equals mc squared? So why was he, of all people, worrying about the viscosity of a suspension of spheres? And the answer is that from the viscosity, the measurement of the viscosity, the change in the viscosity by adding a bunch of spheres to a fluid, you can get the product of Avogadro's number and the size of the object you've added cubed. And from a measurement of the diffusivity of that same thing you added to the fluid, you get the product of Avogadro's number and the size of the object. We're supposed to know the gas constant from kinetic theory of gases. And with those two measurements, we're able to back out what is Avogadro's number and what is the size. And Einstein just dutifully applied that to a sugar molecule, and got a sugar molecule about 5 angstrom in size, and got Avogadro's number 6.56 times 10 to the 23rd. So from a macroscopic measurement, able to measure a molecular atomic property. That's kind of a remarkable result, and that's why he was interested in it at that time. And that's actually why Sutherland was interested in it for the same reason. You can determine macroscopically a molecular property. You know, today we'd be happy to get the exponent to a few significant digits. He got the coefficient out front as well, which is 6.02 in case you have forgotten what a mole is. And as an aside, you know, the astronomers always talk about astronomical numbers. You know, a mole is bigger than most of those things. So we should reclaim the biggest thing. It's a mole is a big number, not astronomical numbers. Okay, and it was a big deal, so big that the Nobel Prize in Physics was handed out in 1926 for the measurement of Brownian motion, because that was taken as definitive proof of the molecular atomic nature of matter. So that's why Einstein was worried about that. And it's a workhorse today, that there are lots of generalizations of this notion of this random walk process, this diffusion, if you can not only for translation, but also for rotation of a particle in a fluid. You can measure its rotary diffusivity, and that's also the thermal energy times its rotary mobility, which for a sphere is inversely proportional to the size cubed of the object. And if anybody who actually is interested in the properties of small particles, the way you characterize their size is actually by measurements of what's called dynamic light scattering. You actually measure the diffusivity, and from that infer the size, making use of this formula here, if you know the viscosity of the suspending fluid. If you don't know the viscosity of the suspending fluid, but know the size, you can use it as a rheometer to measure the rheology, the viscosity of an unknown material. And that's given rise to an area which is quite active these days on microrheology, trying to make use of this idea to measure the viscosity, if I know the size, from measurements of the diffusivity of particles. Now, people often wonder about, can I still apply these formulas? You know, Einstein was very bold and applied it to a sugar molecule and so on. And let me give you a simple reason why it might be good to apply these notions of continuum fluid mechanics down to these colloidal molecular sizes. And so first, a few observations. First is, why do we get to use continuum fluid mechanics even though we're down to the colloidal size? And here I'm thinking about molecules of size B and a colloidal object of size A. And I mentioned before about time scale. So the time scale for the particle compared to the time scale for the solvent actually scales like the size ratio squared. That's for the momentum to relax of those objects. The number of solute particles or solvent particles I have per colloidal particle will scale like the size ratio cubed. That's just to fill space. And if I ask myself how many solvent particles have collided with a colloidal particle in the particle's momentum relaxation time, that scales like the size ratio to the 4th power. All those are just to tell you that all that's important is there's a difference in size between a colloidal particle and the small molecule solvent, and that gives rise to a large separation of length scales, large separation of time scales, and as a result you can make the fluid, the solvent, a continuum and not worry about the graininess of the solvent at all. People often wonder about that, and so here are some results of some molecular dynamics simulations for moving a particle adjacent to a flat wall, and this shows the results comparing the drag I would get from the molecular dynamics simulations, the symbols, to what the Stokes flow no-slip hydrodynamic drag would have been for a particle. Okay? And it works really well. This is a blow up of the region down here. In this case, the particle is only 3 times larger than the solvent molecule. You get the right continuum mechanical drag all the way down to a spacing, that is the distance the particle is from the wall, of 1 molecular size. Okay, so even down to see the graininess of solvent, still the continuum fluid mechanics with the no-slip boundary condition works. Now people realize that today the colloid scientists are getting very clever, and they're making materials which have these super hydrophobic surfaces. So I can make things which slip like crazy. And so where does that fit into this picture? So there's 2 reasons why that fits in, how it fits in. One is to make a perfectly no-slip surface. They're often very large scale, take care to make a flat, molecularly smooth surface. Okay, so if you imagine now taking that molecularly smooth surface, but wrap it around a 100 nanometer size particle, it's no longer molecularly smooth. It's now become rough on the scale of the particle. At the same time, colloid scientists are very clever in being able to graft molecules on the surfaces of things to make it the fluid not stick to the surface. So you can do that to the colloid. Even if it's bumpy, you can graft polymer chains to the surface, and many people do that and make a living of grafting polymer chains and particle surfaces. But if you do that such that the solvent doesn't like the particle any longer, then the particle won't go into solution to begin with, and you won't have a problem. So the only way they become in solution, is if they're wetted by the solvent. As a result, the no-slip hydrodynamic boundary condition works fine. Okay, so that's my reason for that. So everything I'm going to tell you from now on, we're going to use the no-slip fluid mechanical condition at the surface, even for things down to 10 nanometers or smaller in size. And so I have a thing about sizes. So this is one slide, which is, if you remember nothing about the talk, this is the only thing I'd like you to remember. It's a very simple thing to remember all the things you need to know. And let's think about a particle which is a 0.5 micron in size. So its size is 1/2 times 10 to the minus 6. If I have it twice the density of water, it'll fall due to gravity. And the fall speed, when I balance the buoyancy against the Stokes drag, is a 0.5 micron per second. If I calculate the Reynolds number, at a ratio of the inertial to viscous forces, based upon that fall speed, I get 1/2 times 10 to the minus 6. So there's one number, gives me the size, the speed, and the Reynolds number, 1/2 times 10 to the minus 6. These particles are also small enough that they'll undergo Brownian motion. If I calculate the diffusion coefficient from the Stokes-Einstein-Sutherland relation, it's a 0.5 micron squared per second. So again, just one number, 1/2 times 10 to the minus 6, size, speed, Reynolds number, diffusivity. Okay? There's one other number that will be important. That is, as these guys fall, they also diffuse, and there's a ratio of diffusion of convection to diffusion, which is the Peclet number. That's a 1/2. That's not small. That's a 1/2. And that's because that's what a colloid really is. It's particles where the thermal motion competes against the other driving forces. But so that's a simple thing to remember. 1/2 times 10 to the minus 6. You don't have to know KT. Don't have to know the viscosity. You can just figure everything out by scaling from one to the other. Okay? So that's some background, a little history. Now I want to talk about the amazing rheology of spheres, or how to walk on water and make a bulletproof vest. So we start back here. We had Einstein. And in the next correction, order phi squared, it took 70 years. So you have to ask yourself, why did it take so long to add the next order phi squared correction to the viscosity of a suspension of spherical particles? It could be people had other things to do with their life, maybe, but nonetheless, it still took a long time. And there are 3 reasons, at least 3 reasons I can think of why. The first one is the fact that the interactions are very long-ranged. That if I have a particle in a fluid, these particles have no net, they're just neutrally buoyant suspended in the fluid. There are no forces and torques acting on them. But if you put it under a flow, they won't deform as the fluid wants to deform. And that generates what's called a force dipole in the particle, or it's called a stresslet in this business. And that results in a disturbance that's very long-range, decays like 1/r². And if I have to have a lot of particles interact with each other to add them all up, that's a big number. If I add up r³ worth of r², I get too big of a number. And so how to calculate all these long-range interactions was a very challenging problem, which wasn't resolved really until the late 70s, early 80s, of how to do that in a systematic fashion for any two-phase material, actually, not just suspensions. That's one problem. The second problem is I need to know where all the particles are, how they're arranged in space, and that's not given to you. That's part of the problem as well, because as I flow the material, the distribution of the particles, how they arrange themselves in space, how their separations are, and so on, is a function of how they're flowing. And we are not given that. We have to find that as part of the problem as well. And that makes the problem ultimately nonlinear. And finally, there's an additional contribution to the viscosity in addition to what Einstein calculated. Einstein calculated a contribution just associated with the fact that the particles are rigid and don't deform like the fluid. But once I have multiple particles interacting, then the particles want to be randomly distributed in space. If I force them to be in different configurations under flow, they'll try to return entropically back to that random distribution. And I have to do work against that entropic force, and that dissipates energy, and that goes into the viscosity as well. And that's what's called this piece here. So you had to figure out all those three pieces before you could calculate the next correction. And Batchelor did that. This is a picture of George Batchelor down here. He calculated both the change to the dissipation part that Einstein worried about for order phi squared, as well as this additional contribution associated with the entropic Brownian forces in the system. And that's the result there. And so the next term. Do we need to wait another 70 years? And so I was thinking about this, and so to do next time, we're going to do 3 particles, right? So we had 3 interactions, and they're all different in space, and so on. And when I was thinking about this, I was realizing, if you're really clever and you can get something important like Avogadro's number with 1 particle, then you get to be an Einstein. If it takes you 2 particles, you get to be a Batchelor. For the rest of us, I'm sorry, we're down here taking lots of particles to get anything useful about. But if you think about, if I can do 3, you can do n. It's no harder to do 3 than it is to do an infinite number of particles. Of course, the computer's going to do all the work, right? That's who's going to do all the calculations for us. But conceptually, it's no different than doing 3. If I can do an infinite number. And so that's what we figured out. We tried to invent a method which we called Stokesian dynamics, which allowed us to do an infinite number of interactions amongst an infinite number of particles. And so I'm going to briefly describe what the important physics in that is, and then discuss some of the results we have from using that as a way to figure out what happens to the phi cubed and on. Okay, so there's only 1 or 2 slides about Stokes dynamics. So the fluid, the solvent, is described by the usual fluid mechanical equations, and they're going to be at small Reynolds numbers, so we don't have to worry about the inertia. We know what the fluid mechanics equations are, the no-slip boundary conditions. So let's just focus our attention on the particles. The particles have usually Newton's law of mass times acceleration, the sum of the forces. Since the Reynolds number is small, the inertia of the particles is typically small as well. And that gives you an example here. If I ask myself, what's the inertia, what is the time scale for the particle's momentum to relax? The time scale is given by the mass divided by the Stokes drag. For our favorite particle of a 0.5 micron in water, that's 10 to the minus 8 seconds. And you'll find out the particle hasn't moved at all in the time its momentum relaxes to 0. And so I just have a balance of forces. A hydrodynamic force, a fluctuating Brownian force, and then any other kind of forces you might want to have. The hydrodynamic forces, they're at low Reynolds numbers. And so there's a linear relationship between the force and the velocity of the particles relative to some imposed flow, given by a generalization of Stokes drag, that now drag coefficient I call R, is a function of the configuration of the particles. But it's a well-posed problem in low Reynolds number fluid mechanics for what the drag forces are. And when I use forces, I also supposed to keep in mind torques as well. They're hidden inside there because particles can rotate as well as translate. I don't explicitly say that. So that characterizes the fluid mechanical hydrodynamic forces. There are also, as we mentioned, the particles can undergo thermal fluctuations from the solvent, giving rise to Brownian motion. On average, those Brownian forces are 0. This is an average over the solvent. And their correlation is instantaneous in time because it occurs on the time scale of the solvent, which is very fast compared to the particles. And it's given by the thermal energy kT and the same hydrodynamic drag force that appeared in the hydrodynamic forces. That's what's called the fluctuation dissipation theorem. Thermal fluctuations impart motion to the colloidal particle, and that energy is redissipated through the viscous drag. And so it's the exact same hydrodynamics here as there are there. So the hydrodynamics characterizes both the hydrodynamic forces as well as the thermal forces. And then you can have any other kind of inner particle forces or external that you want to have. And this is true no matter what size, shape, color, bounded, unbounded, it doesn't matter. It all can be expressed in terms of just knowing what this symbol R is. Okay? So now I'm going to tell you in 2 slides the 2 important things you need to know about R. And that is the following. So I'm going to focus on the forces between particles. And just think about the simplest case of 2 particles moving towards each other. And I'm plotting that force appropriately normalized as a function of the non-dimensional separation between the particle surfaces. Let's start off here with the red is the total, start off with, I guess, the blue. When the particles are far apart as they move towards each other, and we can solve for the fluid mechanical equations and calculate those forces. We know exactly what they are. Of course, the experimentalists don't believe us, so they have to go do some experiments to compare. Okay, and so these are some experiments done by John Crocker, who measured the diffusion coefficient, the instantaneous mobility, if you will, by measuring the short time diffusivity of 2 particles separated distance. He measured the motion both this way as well as this way, as well as this way, as well as that way, 4 different components. And from those measurements, which are the symbols, compare them to what the solution is for the Stokes flow for those particles for all separation distances, and it works perfectly fine. So experimental measurements that the fluid mechanics is working good, which the fluid mechanicists already knew, but it's good that the experimentalists finally agree. These are particles which are a micron in size, roughly. Okay? So that's one aspect of how particles interact when they're far apart. They're very long-ranged. In this case, if I have a forced particle, interactions decay like 1 upon the separation distance, very long-ranged interactions. There's also, when particles get close together, the force gets very sharp and very steep. There's what's called short-range lubrication forces. And those, if I try to take 2 particles and push them together at constant relative velocity, I have to squeeze out the viscous fluid which separates those surfaces. To squeeze the fluid out, I have to have a large pressure gradient drive the flow. That pressure resists the motion, and the force diverges like 1 over the separation between the particle surfaces. That's what's called a lubrication force. And that has the following important physical consequence. If I put a bunch of particles in a line like I have here, so all just spheres in a line, neutrally buoyant, not touching each other, but very close together, and I push the last particle in the line, the whole chain of particles would translate as a solid object. Of course, you all say, well, that's obvious. Here's a solid object, no fluid mechanics. I push it, it also translates like a rigid rod, of course. However, because of the flow runners over fluid mechanics, if I pull the last particle in the line, they'll all translate as if it's a rigid object because they're connected by the lubrication forces. Okay? That would happen if it's rigid as well, right? So particles being connected, even though there's no force and torque on them except for the last one, they behave as if they're a rigid object just due to the connection of the lubrication forces. And that forces are transmitted from one particle to the next by short-range forces, lubrication, is not transmitted via the fluid out here at all. It's just the connectivity of the structure and these short-range connections together. Okay, and that's another piece of the force which you need to worry about when particles get close together. And that's, of course, a near-field 2-body calculation, which you just don't need anybody else, but you need the connectivity and the 2 particles. A few more things we've got to worry about. What's next? Oh yes, they're long range. So to give you the aspect of the long range and the many-body character, I can illustrate the following way. If ultimately, we're going to want to do some computer simulations. And so we have periodic boundary conditions. And if they're periodic, I have a periodic replication of things. And let me give you an example of what happens if I think about these particles now falling due to gravity. Unfortunately, they're falling sideways instead of down. Gravity is pointing in the wrong direction in Cornell. Yes, okay. No. So, but if I plot the fall speed normalized by a particle by himself, and I just make them point forces, they fall down so rapidly that they fall up. The sedimentation speed becomes negative at a volume concentration about 20%. If I just approximate it as point forces. If I do the many-body calculation properly, then of course they always fall down and fall down more slowly. So that's just an illustration of the fact that we have to worry about many-body interactions as well in order to be able to figure out what goes on. So that's okay. You can just make it a periodic system by putting a star on that R. So that was easy to do conceptually. Okay, so that's all there. That's the physics we have to have. Whoops, sorry, there we go. I'm sorry, I went too fast. There we go. So now we have to do is following is the procedure. We have to implement basically matched asymptotic expansions. That is near field, far field, which are completely different things separately, somehow fast enough in order to analog in operations for millions of time steps so we can then evolve and watch what happens. Okay? And so that's what's involved in Stokes dynamics. And that's been my problem, not your problem to worry about. And so that's all you need to know. So now I'm going to tell you what you can learn by making use of that. Okay? But I'm not going to tell you any more about what goes in there. That's more than you probably want to know. On to the Mason rheology of spheres. So we're going to do periodic boundary conditions. This is a snapshot of something which is sheared, oscillating back and forth. And I can make it the simplest possible system, mimicking what Einstein and Batchelor had done. There'll be nothing but Brownian motion and hydrodynamics. That is going to make the particles be hard spheres, so there's no interaction unless they try to overlap, then an infinite repulsive force. So all that's in the problem are hydrodynamics and Brownian motion and nothing else. So the simplest possible system. There'll be one dimensionless parameter which is important, which is the ratio of the shearing forces to the diffusion, or the Peclet number, which I've written down here is proportional viscosity, size cubed, shear rate, and the thermal energy KT. Okay? And now we're going to ask ourselves what happens to the rheology. So the first thing we're going to do is look at results which are subjected to what's called a very small amplitude but high frequency experiment. So that small amplitude, so you don't drive the structure out of equilibrium, but very high frequency, so you measure the dissipative part of the response. There's also an elastic part, which would be a modulus, but this is just the dissipative part. Sorry, no G double prime for you, just G prime. Right, and so you can do experimentally measure that. And this is what's called the high frequency dynamic viscosity as a function of the solid's volume fraction. That's what Einstein had done, and the next correction was what Batchelor had done. So this is all the rest as a function of volume concentration. The open symbols in green are experiments, and the solid symbols are results of the Stokes dynamics calculations. And there's no adjustable constants anywhere in the comparison between the experiment and the simulation results. So we seem to know how that works pretty well. That's one aspect. That was high frequency, small amplitude oscillation. You also can subject the suspension to a steady shear, but at very low shear rates, and get what's called the zero shear rate limiting viscosity. And that was the other contribution which Batchelor calculated, called the Brownian contribution to the stress, now at small shear rates. And this shows you a comparison of just that contribution as a function of volume concentration. You can also measure that experimentally in the green and in the blue symbols and in the red symbols, experimental measurements of that contribution to the viscosity. And then the solid symbols, squares and circles, are the Stokes dynamics calculations of that, again, with nothing adjustable between the simulations and the experiment. I note there's 7 orders of magnitude in amplitude, which you can track faithfully from the simulations. And you can do it all the way up to what's called closest packing. In this case, the colloid undergoes a glass transition from a fluid to a glass. If you try to pack them high enough, a random close packing will be out here at 60-some%, but these materials stop flowing at a glass, which is about 58% by volume, and indeed you can find the viscosity diverging as you go to the glass transition. Okay? So that was just sort of a baseline. Can we calculate stuff? And so now we're going to take a walk down a particular concentration and a particular shear rate to see what happens as we turn on some flow and drive the system out of equilibrium and ask what happens to its viscosity. And eventually with that we'll be able to walk on water. So there's a punchline at the end. Okay? So this very simple system, we're going to be down here where we have hard spheres, and we're going to walk down a particular shear rate, particular volume concentration, and ask what happens. There'll be 3 regimes, one in which the Brownian motion dominates, someplace in the middle where the two balance, and someplace where the hydrodynamics win, because they have one-dimensionless parameters you might expect. And so here is the results at a particular volume concentration of 45%. The viscosity, it displays what's called shear thinning, as well as what's called shear thickening, as a function of the non-dimensional shear rate or Peclet number. This is the viscosity of the suspension compared to that of the solvent. And we're actually able to separate out the separate contributions that associated with the hydrodynamics. That's what Einstein calculated. And that's what's associated with the Brownian motion. That's what Batchelor calculated. Now as a function of Peclet number at a higher concentration. And we can also map out what the structure is that takes place. So this shows you the microstructure. That's a microstructure, meaning what is the probability density I find a particle here relative to one at the origin. And that shows the first nearest neighbor peak, the second nearest neighbor peak. That's the structure, for those that know structures, characteristic of a liquid-like material. Nice and isotropic structure. As you turn on the flow, you distort that structure to a distorted state here in this shear thinned region, and to another state here in this region where it starts to shear thicken. When we first did these calculations, I was very proud because we managed to separate these two contributions to the stress, right? And the rheologists couldn't do that. They only just measured the total viscosity. And I said, ha, you can do more than you can. We got both these pieces. Of course, once you say, ha, then you get people's attention. And so, of course, Norm Wagner came along and said, no, I can do neutron scattering. And my neutron scattering results, I can back out both the separate contributions just like you had done, and indeed find that the Brownian or thermodynamic stress shear thins, and the hydrodynamic stress results in the shear thickening. And not to be outdone, also Ite Cohen here at Cornell has also done similar experiments with confocal microscopy, being able to confine suspensions and measure both the shear thinning and shear thickening, and actually measure microstructures. I was pleased to see he used the same color scheme that we did pretty much, so things look almost the same. His structures are a bit different because they're confined a little bit, so there's an influence of the confinement on the structure. But actually from measurements of the distribution of the change in microstructure, he's actually able to go in and back out what the viscosity is from direct measurements of what the microstructure is. Okay? So, and so he's actually able to determine both the hydrodynamic and the thermodynamic or entropic contributions to the stress. So that's both good and bad. Bad because, I was really proud we did this, and, so that's just a warning. Don't be too proud. People will show you up soon enough. So that seems to be confirmed both microstructurally as what goes on. And then, so how about compared to experiments? Oh, yes. So there were some experiments done around this time. This shows you a comparison of experiments, the open symbols, against simulation results for various volume concentrations increasing, showing you both the shear thinning as well as the shear thickening. And it's quite remarkable that the experiments and the simulations were all done at the same volume fraction. So it's actually not remarkable at all because the people talk to each other about that. And the reason this came about was the following: was we first did these simulations. We actually were able to first predict that these materials shear thickened from simulations. That was the first observation, that the hard spheres would actually shear thicken. And this shows you the real data, experiment simulation data that, you got to believe what you're doing, of course. It was a long time ago. We had very few particles in those days. But I went and gave a talk to the guys in the Netherlands, and they had all these great shear thinning data, and they thought that was the end. They didn't think it shear thickened at all. That's what the conventional wisdom at the time was. We said, no, the hydrodynamic part's got to shear thicken. And so the Dutch gave it over to the Belgians, and they made bigger particles, because don't forget, you have 7 orders of magnitude in shear rate range you must access, so they needed larger particles for the experimental apparatus to be able to see the shear thickening. And sure enough, they were able to see the shear thickening again, just as we had predicted from the simulation results. So that's why the numbers all sort of, the volume fractions, everybody talk to each other. So now let me give you a mechanism for why it shear thickens. And the mechanism that we came up with was what's called hydroclustering. And I'm going to give you a very simple-minded argument about why that happens. Much more simple than I think we've ever written down before. As we saw, all the increase in viscosity came from the hydrodynamic contribution to the stress, not from Brownian motion. Okay? So I'm going to focus on the hydrodynamic stress. And just by dimensional analysis, the hydrodynamic stress scales like the viscosity of the solvent, the shear rate, and the particle size cubed. Okay? And so the viscosity goes like the solvent viscosity, the particle size cubed, times the number per unit volume. That's the change of viscosity. And so the question you have to ask yourself, if I have only hydrodynamics, how can I change the viscosity? Keeping the number of particles fixed, their volume fraction fixed, and so on. How do you get the change? If I took those same particles and I were to compact them together in a compact aggregate, so now I have one particle of size b. The viscosity is eta b cubed 1 over volume, but they're compact. So the number in per size b goes like n to 1/3. I haven't changed the viscosity at all. So hydrodynamics alone, if I just rearrange them and pack them together in compact clusters, you'll never be able to increase the viscosity. The only way you can get the viscosity to go up from hydrodynamics alone is making non-compact clusters. So I make small things which grow into large aggregates, and then the viscosity grows like the length cubed, and now you can make the viscosity increase as the shear rate increases. And that's the result for what's the hydrocluster mechanism for shear thickening. You must grow clusters which are larger than particle size in order to increase the viscosity if all you have working for you is hydrodynamics. And with that knowledge then, you can ask yourself, if I turn off the hydrodynamics, they don't shear thicken. And actually you can see that by some simple calculations. If I were to now make particles which are hairy, so they can't get very close together, so I turn off the lubrication forces, then they just shear thin, they won't shear thicken. And that's actually known experimentally as well. If you add a little dash of an important material to the surface to prevent the particles from getting too close to each other, you'll turn off the shear thickening as well. And that's actually been well known. The people will sell you at a high expense a small magic powder to increase the flowability of your suspensions. And that's what they're doing. Okay? But you can go the other way. If you actually jam them together closely, overcome this repulsive force, they'll suddenly shear thicken as well. And that's been seen in the experiments also. So now, the amazing part. How do you walk on water? Okay? So cornstarch in water is nothing more than particles in a liquid. And it's well known that cornstarch gives rise to what's known as the shear thickening fluid. And we have an example here on the left. There's a large container of cornstarch, large, that's a cement mixer in the background. And you can walk on it. It's a shear thickening fluid. I'll let that run as you can watch them walk on water. But if you're really smart, which Norm Wagner was my colleague and friend, not I, you can actually make a bulletproof vest. That is, you take normal Kevlar and impregnate it in a shear thickening fluid, nothing more than cornstarch and water, actually more sophisticated. You've tuned the particle size to give you the right temporal response. The bullet bounces off, okay? Just by making use of the shear thickening nature of the material. I often like to think of this as, you just send this video clip to the grant awarding body and they send you money back the other way. You don't have to write anything down, just send the video clip, okay? All right, so do we have time to do how diffusion demixes suspension? It's up to you guys. I know it's kind of late. But okay, I'll go through it even more quickly than I went through the previous part, but where's the clicker? So I'll try to be quick about this. So go back to the beginning, talked about Brownian motion of these guys. So there we are again, where we started from. Brownian motion gives rise to mixing. So I have two containers, red particles on one side, blue on the other, and let them mix. They'll mix, and the time scale to mix is the length squared divided by the diffusion coefficient. That's sort of a well-known kind of thing. And so if you think about how long it takes things to diffuse, so we talked about it before, and one way to think about diffusivity, which I want you to also think about, is the diffusivity goes like the velocity fluctuations squared times the correlation time. In the case of Brownian motion, the velocity fluctuations are actually thermally driven, so they're kT over the mass. The correlation time is the mass divided by the drag. Within a factor of 3, you get Stokes-Einstein Sutherland. And he mentioned before, for a half-micron sized particle, it takes a second to diffuse its size. If you pack a bunch of particles into suspension, they diffuse more slowly because their neighbors are around them. And this shows you a plot of the diffusivity normalized by the dilute value as a function of volume concentration. It goes down, and there's a lot of data here. Open symbols are experiments. The triangles are Stokes dynamics calculations, again, with no adjustable anythings. For those that paid attention before, that curve sort of looks like the inverse of the viscosity curve I showed you, and so that's the inverse of the viscosity curve that I showed you before. There's an interrelationship between the high frequency dynamic viscosity and the short time self-diffusivity. They're not exactly the same, but for government work, they're the same thing, okay? Similarly, there's a long-time diffusion coefficient, which is shorter than the short-time diffusivity because I got to push my neighbors out of the way. And that plunges, again, goes to 0 at the glass transition and so on. So those are interesting things. So that's just to show you that as I add particles in solution, their Brownian motion is hindered hydrodynamically and sterically, and diffusivity goes down. Okay? That's what you're going to take away. And so if you ask yourself, even without that effect, a particle of half a micron takes a second to diffuse its size. A particle of 5 micron takes 1,000 seconds. A particle of 500 microns takes 10 to the 9th seconds, which is 30 years. And they all can be reduced by several orders of magnitude if the concentration is increased. So that makes you wonder if I have particles which are, say, 10, 20 microns in size, and they're very concentrated, they're not going to go anywhere at all. And maybe if I stir them instead, I can get them to diffuse. And so if I apply a shearing motion, perhaps I can get a different type of diffusivity associated with the shearing motion rather than the thermal motion. And that's called shear-induced diffusion. Just by dimensional reasoning, the velocity fluctuations go now like the shear rate times the particle size squared. Correlation time is inverse shear rate. That predicts a diffusion coefficient, which goes like the shear rate times the particle size squared. So it seems like stirring might give rise to diffusion as well. And so let's explore whether that happens or not. It may seem intuitively obvious, but then there were some experiments done by this famous gentleman here called G.I. Taylor. So I'm going to play this little video clip for you, and you can see, and hopefully the sound will be up there as well, since you can hear his nice accent. So these are low Reynolds flow. It has another property. That property is called flow reversibility, and that one may make you wonder or not whether shearing causes things to diffuse. Can you hear this?
Plays only a very small part in the conditions which determine the motion. Here are two concentric cylinders. The fluid can be moved by turning the inner cylinder with this handle. The annulus between them is filled with glycerine. Into this space I introduce some dye, which stays put owing to the high viscosity of the glycerine.
There we go.
Note its position before I start turning it. I now turn it 4 times, pushing the handle clockwise. The dye seems to mix as a drop of milk mixes when it is stirred into a cup of tea.
It's British, after all, a cup of tea, right? Now watch, pay attention.
Now I reverse the direction.
Now you got to pay attention here, where the red dot is.
Turning exactly 4 turns, the dyed area reappears in its original position, with a little fuzziness due to molecular diffusion.
There we go. Okay, came back. There we go. And you can see this in E.T. Cohen's lab. You can see it in real time, I believe, right? You can do the experiment yourself. And so now that makes you wonder if we have the diffusion was a random process, and here we're going to try to shear these guys and diffuse, but then G.I. Taylor just told us they don't diffuse, and so it's not really clear whether they diffuse. So I thought I'd let you decide. Okay, we're going to put it to a vote. So I'm going to show you the results of 2 simulations. One simulation, they're both 35% by volume, both a small Reynolds number. One simulation is just Brownian motion. One simulation is no Brownian motion at all. And it's going to be, the shear is going to come out of the plane at you, so you can't see the shear motion. And we're just going to tag one particle center. Okay? And so everybody pay attention, because you're going to be asked to vote as to which one is diffusive, which one's Brownian, which one's not. Okay, I think it's going to stop in a second there. There we go. Okay, so how many say run A is Brownian motion? On vote. Wait, don't be bashful. How many say run B is Brownian motion only? It's about half and half, which is good, because you shouldn't be able to tell which one is which. Okay? People always try to divine something special about one versus the other one, and you can't tell at all. I've strobed it. Now I'm going to show you the same results, but at a finer time scale. And now you see the one C, which I presume was the previous one. I don't know which one was it, honestly. You can now see its trajectory is deterministic, but at longer times, when I strobe it, I just see Brownian motion, whereas this one's always Brownian, no matter at what time scale that you see it. Okay, so that's just to let you vote on. It undergoes random diffusion. And there was another experiment that was done by my colleague Dave Pine and Jerry Golub, repeating G.I. Taylor's experiment of rotating in one direction and then rotating back again. Okay, but now for a concentrated dispersion of colloidal particles, in which some of them have been dyed black. There's a lot more, concentration like 30% by volume, but just showing a few of them, they're black. And they're going to strobe this just at the period. So go back, go forward, go back, and take a picture each time we come back. Okay, so the left hand will be at small strain amplitudes. And so you see a little bit of tiny motion of the particles, but basically I go one direction, the particles are displaced a very large amount like G.I. Taylor did, but then you come back and the particles all come back to where they were before at a small strain amplitude. If you up the strain amplitude too large, they diffuse. Okay? So they do seem to undergo a random walk. And that is a result of the fact that the motion, the equations of motion of the particles are very highly nonlinear and give rise to what's called deterministic chaos. And if you actually plot how 2 trajectories might diverge, there's a quantity called the Lyapunov exponent which measures that. And that stays very small if the amplitude is small. But once you reach an amplitude of a strain of about 1, then this Lyapunov exponent grows rapidly and 2 trajectories diverge. And diverging trajectories will give rise to chaotic motion and give rise to random process and random diffusion. And indeed, you can measure then that diffusivity. And so we did simulations of the diffusivity. This shows you under flow, the same condition we had before, but now measuring diffusion, the self-diffusivity, normalized by the infinite dilution Stokes-Einstein-Sutherland value. Down here is what we talked about of the long-time diffusivity in equilibrium. Now turn on a flow, and sure enough, it starts to grow and scales as the shear rate particle size squared at higher concentrations. And it doesn't depend too much on whether you measure it in the velocity gradient direction, the vorticity direction, or even the flow direction. So it's not that anisotropic. If you look, I'm just going to talk about things at this limit here at infinite Peclet numbers, not this stuff down there. If you look at the displacements, you find that initially it grows like time squared. Initially it's ballistic until I've waited long enough for it to have forgotten where it came from, and then it grows diffusively at long times. And people have made measurements of this as well, and make measurements of the diffusivity in the velocity gradient direction, normalized now by the shear rate particle size squared, for a bunch of different particle sizes, a bunch of different viscosities, a bunch of different shear rates, and they all collapse together onto one curve. If you're in the eye of the beholder, it's one curve, okay? So that's the data. And so we did it once and we did it again, and we could never quite get an agreement with the experiments. These are quite good experiments. But nonetheless, we compared against the experiments which were done by Breedveld et al. And they had, this shows you the mean square displacement as a function of strain. And those are their experiments. And the blue line is their simulation results, which agree perfectly. And as a matter of fact, they took their data and they drew a straight line through the data. And that's the diffusivity they reported. Unfortunately for them, that's as far in time or strain they could go. Simulations, we can go much further in strain and time, and they have not reached the long time limit yet for their diffusive process. And so, you know, I would draw a straight line through the data too. Everyone would, right? It's good enough, but they're not quite at long time, and so the diffusivities that we report at long times are actually smaller than what they had reported because of the limitations of the experiment. They couldn't do longer experiments, but we can do shorter simulations. And so we can do the same time frame that they do, and what kind of diffusivities do we then report from the same time interval. And now it agrees with the experimental results. And so these are actually, actually in agreement then in that sense. They all agree with each other. A liberal interpretation there, right? Yeah, excellent. But the important point I want you to take away is the fact that this diffusivity increases with concentration. In the Brownian case, the diffusivity decreased with concentration. Now it increases because I need collisions to diffuse. Without any collisions, they don't diffuse. Whereas in a Brownian system, collisions restrict and hinder my motion. So it changes in a qualitative way. Not only does it change in a qualitative way, it also scales differently with the size. Here the diffusivity goes like 1 over the size. Here it goes like the size squared. So I just leave this out for those, maybe this interesting regime in between where it no longer is size dependent and it's no longer concentration dependent. Okay? Where does that space live? Okay? I know it's running late, but I want to one last thing before we go, and that is random things usually mix. So why does this shear-induced diffusivity demix something? Okay, that's the puzzle, right? But this diffusivity is proportional to the shear rate times size squared times the diffusivity. And so if the shear rate varies, then particles will move from regions of high shear rate to low because the diffusivities are different in those different regions. And as a result, if you have pressure-driven flow in a tube, all the particles move to the middle. So spontaneously, on their own, just via interactions, they move to the center. And this shows you results from experiments by Jim Gilchrist with confocal microscopy. Shows you concentration. Here's the walls. It's diluted near the walls and concentrated in the middle. These particles have migrated away from the walls just due to this shear-induced migration. So even though they diffuse because they're sheared, that diffusion results in demixing rather than mixing, which is a funny kind of thing to happen. And you can do experiments that Lyon and Leo had done to measure the migration and measure the concentration profile as peaked at the center rather than being at the walls. I know it's been a long day, so active matter, that's discussion for tomorrow. We'll talk about these things tomorrow for those that want to come back and hear about how things that move themselves behave. And I invite you tomorrow to hear that. Let me just conclude with pictures. It's a lot of stuff, even a tiny little sphere. The Hubble sphere has a very interesting rheology and diffusivity character, which is quite surprising. And you can only imagine now when people can make all kinds of shapes and functionality, what more fun we can have in trying to figure out how these things go on. And I'd be remiss if I didn't sort of acknowledge the PhD students who've worked over the years, and postdocs, collaborators, and funding who have all helped me over the years in this project. And so with that, I want to thank you for your attention.